Hello Physics 20s, let's look at resonance and standing waves, which is our 7th lesson here in the final unit. Alright, before we get into it, let's look at sound, something we're all familiar with. And that's not what I want. And the different characteristics of the waves that affect sound. So remember that sound is a longitudinal wave. It has these compression waves in the air molecules. The pitch, so that's how high pitch or low pitch it sounds, right? Whether it sounds high or low is dependent on the frequency of the sound, right? So how fast our waves are actually changing from troughs to peaks, or compression zone to rarefaction zone, right? So pitch has to do with the frequency of our source, right? And frequency won't change no matter what happens to it. Changing medium, changing speed, frequency will stay the same. Well, loudness, on the other hand, is related to the density, the amplitude. So when we're looking at our longitudinal waves, right, density is actually represented by our amplitude. So when we have a lot of air molecules occupying this same space, right, the more dense those air molecules are would be the equivalent to a higher peak of our amplitude of our wave. So that would be the equivalent of a louder sound, right? As more of these air molecules are actually hitting your eardrum, because it's a denser wave, that's going to sound louder, right? In your eardrum, you have your membrane, almost like a little drum, that's going to be vibrating as the air molecules collide with it. So having more of those air molecules from louder with more density or amplitude to the sound waves is going to trigger our brains to recognize that that sound is actually louder. And the final idea or characteristic we're looking at is the quality of the sound. And this one is the most complicated. It has to do with the type or nature of the sound wave. So we can actually have some square waves that will sound kind of gross versus a nice smooth sound wave. You can have triangular sound waves. All of those will have different qualities of sound, right? And you can have different overtones to this, different harmonies. So quality is more complicated, and it has to do with some higher level physics, but it is kind of that third characteristic that we will briefly look at. All right, resonance. This is a new topic, a new idea, and it's a little tricky to figure out conceptually. I'll try my best to make analogies that you're hopefully able to figure out. So we need to first realize that each object has one or more natural frequencies that they want to vibrate at. So a spring with a certain thickness and spring stiffness will have this natural frequency where it'll vibrate at. So that kind of makes sense. If we have a really thick spring and we're moving it up and down at a certain speed, it's going to have this natural frequency of the wavelengths that will be different than a thin, lighter spring. So natural frequency is unique to each object. It doesn't have to be a spring. You can even have this with musical instruments, the strings on musical instruments, or even a glass of champagne, which can have a natural frequency. So that's where it wants to vibrate at. That's just how the molecules, the atoms, the crystal lattice is arranged. It will want to be vibrating at that natural frequency. When our periodic force, so this is where we need to bring in an analogy, and I will use somebody on pushing a child on a swing. So when the periodic force, whatever that might be, right, something that's applying a force to our object when that force is applied to the object with the same frequency as its natural frequency, when the force and the vibration are in phase, the amplitude will increase. And I'll just pause and show you this little video. So this man pushing the child, the man is our periodic force. And this child on the swing has some natural frequency, right? Dependent on the length of the swing, the weight of the child, right? It's going to be rocking back and forth at this natural frequency. And as long as dad here, the periodic force, is in sync or in phase with the swing of this child, he can give her more amplitude. Now imagine if he tried to push her when she was at this point in the swing, right? That would be pretty disastrous for both of them because our periodic force is now no longer in phase with the object's resonant frequency. And you could have a total canceling or total destructive interference of our wave here. So it's important that we know the natural frequency where she wants to be swinging at, and we're applying our periodic force in phase with that. And you can see we can gain amplitude every time we do apply that periodic force at the appropriate time in phase with this child's natural frequency or swing. Hopefully that makes somewhat of sense to you. So this response, the increase in amplitude, is called resonance. So him pushing her on the swing at the perfect time with the same frequency as her natural frequency will increase her amplitude, and we call that case resonance. Or we could look at somebody rocking a car to get out of a rut. As long as you're rocking in the natural frequency of the car and its shocks, will increase that amplitude and eventually, hopefully, get out of the rut. And I'll link a video to show how this needs to be taken into account into the design of bridges, right? Propellers, turbines, etc. Anything that vibrates or has the potential to vibrate, we need to think about its natural frequency and limiting the amount of periodic force that could be in sync, right? If we don't, then the amplitude of the vibration can increase and the structure can be damaged. So there's a really good video I'll post about a bridge that kind of had some resonance take a turn for the worst. You'll have to watch it to find out. It's one of the best videos of the year, if I do say so myself. All right, moving on from resonance. Resonance is super important. Make sure that you are clear on what we're talking about with resonance. You can watch some additional YouTube videos if you want. You can email me for a deeper discussion or working on your understanding of that. But moving on to standing waves. So a standing wave, just like the name says, is a wave that looks like it's standing in place, that it's not actually moving. So it's a very unique wave pattern that doesn't appear to move. It's created when two identical wave trains move towards each other and interfere. So what that means is if we have one wave created at this end, we have a wave pulse like this traveling to the right, and at the same time we have a second wave created here and moving to the left. They're actually going to continue to oscillate and generate waves, and those wave fronts will eventually come into contact with each other and interfere with one another. So when these identical waves move towards each other and interfere, we're going to have different types of interference depending on where in that wave train that collision is taking place. So a node where we're actually back at our equilibrium, where they've completely canceled each other out, means we have fully destructive interference, zero amplitude. So that would be like this wave's crest meeting this wave's trough. Yeah, that's where the crest and the trough meet. That'll be a node. Where an antinode is the opposite of that. It's fully constructive interference. That's where the trough of one wave meets the trough of another, and we get maximum amplitude. Right? Peak meets peak, trough meets trough. Here's just a little video, hopefully gives you an idea. So that's just a regular pulsing wave, right? It's traveling there, it's coming back. Now, if he were to move faster, he'll be sending one there, and the fixed end will be sending one back. And when they are perfectly in phase and we have peak meeting peak, we get this antinode, this A. And that's the furthest point out. Kind of have to imagine that his hand really isn't moving, which is a little tough, but if his hand were actually a fixed point, that would be a node, right? And we now have another node there. So we're going to look at harmonics in a bit. I just want to focus on this idea that we have one wave traveling there, right? So this wavefront would actually continue there all the way to the other side and then travel back. But at the same time, we have a second wave traveling from here back towards us. So when both of the peak and the trough meet, we form a node in the middle. Right? So we have a node at the end here, antinode in the middle. Now we have two nodes, which is actually known as the third harmonic. But we'll talk about that in a second. So it's kind of hard to conceptualize, kind of hard to wrap our heads around the idea that even though it looks like the waves aren't moving, that they're just standing and bouncing back and forth, we actually have one set of waves traveling to the right and an identical set of waves traveling to the left that are going to cause these nodes and antinodes as they constructively or destructively interfere with each other. And the distance between each of our nodes is 1/2 of a wavelength, right? Distance between two peaks, that's a wavelength. Half a wavelength would be between this point where the wave's about to start going down and this point where it's about to start going up. So we can use this idea of standing waves and harmonics to look at stringed instruments. So many objects have only one natural frequency. Stretched strings, like that spring we saw here, have many. So when a string is plucked, many frequencies are created. The frequencies that match the natural frequency of the string create standing waves and last longer as the other frequencies interfere and die out. So that's why, depending on what thickness, what tightness of string we're plucking, depends on what frequency we're actually going to hear lasting and resonating with our stringed instrument. Whether you're thinking about guitar, piano, violin, it's the same for all of them. So the standing waves resonate, creating loud with increased amplitude. Whenever we're talking about loudness, we're talking about amplitude. Sound. So they are resonating, which means they're increasing amplitude, right? The periodic force applied to them is matching up in phase with our natural frequency of the string. And you can further amplify that, make it even louder by using a box like a guitar or a surface like a piano. So we don't have to get too far into this. It's just a really cool connection for any of the musicians out there. So the natural frequency of a string is affected by its thickness and its mass. So thicker strings have a lower frequency. It's also affected by the length. Longer strings have lower frequency. And finally, affected by tension, right? Higher tension, higher frequency, higher pitch. So That's all having to do with the natural frequency, as when you pluck a string initially, it's all vibrating crazy. We produced tons of many different frequencies, but it is the ones that match the natural frequency that will actually create our standing waves and lead to resonating, creating those louder sounds that you really hear. So the natural frequencies of a stretched out string, we're going to be looking at these kind of diagrams a whole lot, so we're needing to be familiar with our diagram, right? Node, antinode, node. We've got the length of the string being equal to half of a wavelength, because if we were to continue this half circle oval looking thing, it would become a full wavelength at this point. So twice the length of the string is one wavelength. The length of this string is only half of a wavelength. But if we have it so that it's vibrating like this, which is actually called our second harmonic, then we have the length equaling 2/2 or one full wavelength. So the fundamental frequency of any string that's vibrating is represented as n equals 1, our first harmonic. So that's another thing you might want to get down. Fundamental frequency is also known as the first harmonic. And this is going to be our lowest or smallest frequency, and it's equal to that lowest natural frequency of our string. Because if we had any higher of a frequency, right? Frequency is how many cycles per second. This would only be, right, half a cycle, whereas this would be a full cycle in the same amount of time. We actually have a higher frequency as this second harmonic. So just visually looking at this first harmonic, that string, that standing wave that's going to be vibrating back and forth, will appear to create one single loop. And it'll be the lowest natural frequency. So you'll either see it as F1, our first harmonic, or F0, our natural frequency. Now the second harmonic, we have n equals 2, right? And one way you can think about it is n equals 1 creates one loop, n equals 2 creates two loops for a second harmonic, and the length is now equal to one wavelength, or 2 half wavelengths, right? That could just be simplified as one wavelength, lambda. And the frequency that this must be vibrating at is equal to 2 times our fundamental frequency, because we're actually, right, vibrating twice as fast as this one. We have twice as many oscillations, twice the frequency, twice the cycles per second. And you can expand that into any number of harmonics. It'll follow those same rules, right? Our seventh harmonic would be 7 times the fundamental frequency, and the length will be 7 half wavelengths, and we would form 7 loops. And the speed is going to be equal to that frequency of the nth harmonic, right, with n number of loops times the wavelength of that. Because as our frequency increases, our wavelength will decrease. So let's try out some examples, keeping this diagram and this idea of our wavelengths in mind. So, first question, we're looking at an 85 centimeter string in the fourth harmonic. So we got to get pretty good at drawing these. Fourth harmonic means we're going to be having 4 loops. That's 1, 2, 3, 4. 1, 2, 3, 4. So n is 4. We're in our fourth harmonic. The total length of this guy is equal to 0.85 meters. Now, we know the wave speed is 140 meters per second from the question. We want to determine our source frequency. F is equal to our unknown. So here we would actually be looking at the frequency of our fourth harmonic, as the source will have to be vibrating fast enough to create our fourth harmonic, right? Our 4 different loops. 1, 2, 3, 4 loops. So we're using our universal wave equation. In order to do this, we need to solve for our wavelength. This is what we're looking for in the end, but first we need our wavelength. So if each of those is half a wavelength, and we have 4 of them, our length is equal to, this is just our general equation, our harmonic number times half the wavelength. So we've got 0.85 meters is equal to 4 times half our wavelength. If we're trying to solve for this, we're going to divide both sides by 4 and 0.5, or multiply those together, we get 2. Wavelength is equal to 0.85 divided by 2, or 0.425, right? Or we could just look at the graph and see we've got 1 wavelength, 2 wavelengths. So if 2 wavelengths equals 0.85, 1 wavelength equals 0.425. Right, we have our wavelength now. Let's figure out our frequency of our source. So the frequency is equal to the speed of the wave divided by that wavelength, which is going to be 140 meters per second divided by 0.425 meters, giving us 329 hertz. 1 over seconds is a hertz. Okay, let's move on to our next question. When the source frequency vibrates at 512 hertz, so they're now telling us our frequency is 512 hertz. A stretched string resonates at the 7th harmonic, so n equals 7. What is the next resonant frequency? We're looking for F8. That would be 8 comes after 7, our next frequency. So we're looking for our fundamental frequency. So this is actually our frequency of our source in the 7th harmonic. That's our F7, where the frequency of the source in the 7th harmonic is equal to our harmonic number times our fundamental frequency. So here we have our fundamental frequency is always going to be equal to our harmonic frequency divided by the harmonic number. So our source, or our harmonic frequency, is 512 hertz, and we're going to divide it by 7. And that'll give us a fundamental frequency F0 of 73.14 hertz. And why do we have to find the fundamental? Because we need to know how much to step up from 7 to 8. So this is our fundamental frequency. Our next harmonic will be the 8th, which is going to be and F naught, which will be 8 because it's our 8th harmonic, times our fundamental frequency of 73.14 hertz, which is 329 hertz. So it's 73 hertz more than 512. That should be 585. Sorry. Something did not seem right. 73 more than 512 is 585, not 329. Okay. Hopefully they didn't throw you off too much there. Just checking to see if you're still awake. We've got another one. Now we have a 70 centimeter stretched string. So it has a length of 0.7 meters. And it's working in its fundamental frequency, and is 1. The fundamental frequency is given in the question as 262 hertz. Now we're going to do some weird stuff to this string. We're going to cut it to 50 centimeters. Same string, different length. And we're going to find its new fundamental frequency. I'll use this little apostrophe, which means in physics prime, or that something has changed. And that's my new fundamental frequency of this new length. So we got to do some cool formula manipulation to figure this one out. If we know length, right, we can find out our wavelength. If we know wavelength and frequency, what can we do using our universal wave equation? Speed is frequency times wavelength. We can find the speed. And even when we cut the string, are we changing the medium? No, it's the same string, it's just a different length. Remember, the medium has to do with the molecules, right? The crystal lattice structure of our string or whatever the wave is traveling through. So in this case, we have the same medium. It's like having the same spring thickness. Same string thickness, just different length. So we need to find our speed of the original string. Find V of original, which will actually be the same as the speed in the other one. And we're going to do that by using our frequency times our wavelength. So first of all, length of the string is equal to our frequency harmonic number times half of the wavelength, right? Or we could just extrapolate this and see that 0.7 meters is half a wavelength. Therefore, 0.7 is equal half a wavelength, or in this case, our wavelength is 1.4 meters. Now, the speed is equal to frequency times wavelength, or 262 hertz times 1.4 meters. We get 366.8 meters per second. So that speed is the same speed since the tension and the medium stay the same, right? So speed stays the same. That's the most important thing to keep in mind when we're working on these cutting a string type of question. Speed is our constant. So in our second example, we now have a wavelength of 1 meter, because we've cut it from 0.7 to 0.5, we're still in our fundamental frequency. That's what the question wants us to figure out, right? So in the fundamental frequency, our wavelength is twice the length, or 1 meter. So from our speed, or universal wave equation, speed is frequency times wavelength. We can find our frequency as speed divided by wavelength, which is going to be 366.8 meters per second divided by 1 meter. Meters will cancel out. We're left with 1 over second as our unit, which is hertz. We get 367 hertz as our new fundamental frequency. That's it. That's all. The rest is up to you with the homework. Good luck. I'll talk to you later. Let me know if you have any questions.